Okay, so in this last part of the third lecture, we are going to introduce the Cauchy transform and the Stieltjes inversion formula. These are going to be central for the rest of the course. So the Cauchy transform is the analytic way of understanding a distribution. And as I hinted before, it connects moments and the measure. So these are the two ways in which we study distributions, right? Moments is the way we will study them using free probability, and the measure is something you want to, understand at the end of the day after doing the combinatorial work in the free probability world. So let's just get right to it. Let's start by discussing the Cauchy transform. So I'm looking at this definition. So say you have a probability distribution, probability measure on R. We are only going to think of probability measures on R, but you can extend these things. And the Cauchy transform of mu is a function, a complex valued function. It's defined over the upper half plane, upper half complex plane to the complex plane, and it's given by the following map. So a point z in the upper half plane is mapped to this value. Namely, you integrate the function 1 over z for the input z minus t, where you integrate with respect to t according to the measure mu. Okay. So first of all, note that this function is Lebesgue integrable, so it makes sense to put the integral and so forth, because as we assume that t is, or mu is a probability measure on R, and z is taken from the upper half plane, namely its imaginary part is positive, in particular it's non-zero, z minus t is never zero, and so 1 over z minus t is a continuous function, so it's integrable, it's Lebesgue integrable, everything's good. Makes sense to look at the integral. One easy thing you can check is that, it's really a calculation, is that the Cauchy transform of mu actually maps the upper half plane to the lower half plane. Okay? And another thing you can do, and Gal did that in the recitation, the first recitation, which actually didn't record, but it's an easy exercise. You can show that G mu is analytic on a C++. Okay? You can just find the derivative and see that everything works out. Okay, so that's the Cauchy transform. So a bit of philosophy about this. So, I mean, mu is a distribution, and the distribution is or measure, right? Probability measure. And the probability measure is quite, an abstract notion. It's not so easy to work with. You have at the very abstract level, you have the sigma algebras and so forth. And you don't work like that. Kind of in the less abstract setting, mu, you can think of it as a function, mu of t, even though we said that, for example, when you try to understand the Dirac measure, you can't really think of mu like that. But even in case that you do think of mu as a kind of a plain old density measure, it's still not so easy to work with. It encodes the information that you want to encode. Namely, for example, mu of AB, the open interval AB, is the probability to fall in AB, but it's not easy to work with. What will be easy or easier to work with is this thing, because G mu is an analytic function. You can do things with it. You can evaluate it. You can take its derivative. You can do Taylor expansion around points in which it's defined and so forth. And it turns out that this complex analysis type freedom will allow us to get a better control over the mu via the Cauchy transform. Okay, now the first thing you want to make sure that you can do is that you can actually restore mu from G mu, right? So you want to be sure that the Cauchy transform actually encodes mu, in that you can revert. You can go from G mu to mu. And indeed, that's the kind of one of the main advantages of the Cauchy transform. I mean, first of all, it's an analytic function, so it's nice to work with. And secondly, you can always kind of go back. You can get mu back. But it's not trivial to see how. So, I mean, if I give you g mu as a function, so I'm not giving you d mu t, I just allow you to, evaluate g mu at every point that you would like. It's not clear how to get mu back. And indeed, that's a theorem. And this theorem is called the Stieltjes inversion formula. I think that's a Dutch name, so I probably don't pronounce it correctly. I'm sorry. Informally speaking, the theorem tells you that you can recover the probability measure mu from the Cauchy transform. So it kind of, if you look at this figure, then obviously from u you can go to g mu, but okay, the obvious direction is the non-obvious direction. So from mu, obviously you can go to g mu, but the non-obvious thing is how you to go from g mu back to mu. So let me be more precise. So I want to show you how you can restore mu, and it's enough because it's enough to show you how you can compute, given g mu, how you can compute mu of any open interval. Okay, ignore this bit for a second. We'll get back to it. But essentially, if I'm telling you that how to compute mu of an open interval, then because the open interval generates, this is a generating set for the Borel sigma algebra, knowing the measure on open intervals determine the measure on any measurable set, right? And in general, you usually also work with open intervals or things like that, maybe closed intervals or finite union of those and so forth. So I'm going to tell you how to compute mu of the interval AB, again up to this little bit, using the Cauchy transform. And it looks like that. So it's maybe a bit scary at the beginning. So what you do is as follows. So there is this nice normalization which you can ignore. It's not really important at this point. So what you do is you choose an epsilon that's small but positive, non-zero. Okay, and in my mind, what's going to happen is that this is the complex plane. The measure mu sits here somewhere, right? So it looks like that maybe. That's like the probability measure at every point. And you pick some epsilon, some height. This is the I-axis, the imaginary axis, and so forth. And this line, which is parallel to the real axis, is fine. You can evaluate g mu at that line, right? Because the poles of g mu are only at the real line, if any. So what you do is the following: for the given epsilon that that I'm fixing, the small epsilon, I'm integrating from A to B, the A and B that I want to figure out the measure on. And I'm integrating the following. I'm integrating the imaginary part of g mu evaluated at x plus I epsilon, where I integrate like classically according to x, right? Like just dx, no d mu's. Okay, so in a sense, I'm kind of I'm taking a point here. So that's a point between maybe A and B. So A and B are here. This is A plus I epsilon and so forth, but from A to B. And I'm integrating this function, g mu, at that point, on that line. Okay, it turns out, and you will see exactly why, this recovers the measure of the measure mu at AB. Actually, this is the bit that I kind of try to ignore. You don't quite recover mu of AB. You also add the measure of the singletons. They are called atoms. A and B, if they're non-zero, they're called atoms. Mu of the point A and the point B, right, up to a factor of 2. Okay, usually this will be 0 anyhow, but I'll get back to that. But essentially, if you ignore that, and again, I'll get back to why you essentially can ignore that, you can see from that indeed, because you can restore mu from G mu, it means that whenever you have two measures, mu and nu, such that their Cauchy transform agree, then this means that the measures are the same. So again, this is kind of a magical theorem. It tells you that, I mean, I don't know what's the picture you have in mind, but the picture I have in mind is that you have the measure here, and you really want to understand these heights, right? For example, if this is A and this is B, then this area kind of going outside of the iPad is the thing you want to understand. And what you do is you take a small epsilon, in the sense that when you take the limit, you take a small epsilon and integrate your Cauchy transform, or rather its imaginary part, on this line. So the closer and closer you get to the real line, the better and better your kind of, I don't know, approximation you have, and the limit you actually get you with no error up to this bit. Okay, so let's see the proof. It's a non-trivial and very cool proof. We will use much of what we learned in measure theory and slightly more. So let's see. So let's start from here. So this is the integrand on the left-hand side. Let's just open it up for a second. So what is the imaginary of the Cauchy transform evaluated at x plus I epsilon, where now I'm fixing x and I'm fixing epsilon? Well, according to the definition of the Cauchy transform, I should take the integral, the imaginary of the integral, but I cannot switch them because you can do that, of 1 over x plus I epsilon minus t d mu t. So that's what's written here. But note that I just kind of flipped the minus t and the I plus epsilon, because now this is real, and also the epsilon is real and positive. Okay. Now, the imaginary part of this fraction, in order to see exactly what it is, let's multiply by the conjugates. Right, so this is what happens here, which is equal to that thing. And so from this, you can see that the imaginary part is exactly, this thing. So the minus goes outside, and then you have the epsilon sitting here, and then you have this denominator. Okay, so the integrand itself, the imaginary part of the Cauchy transform, is exactly this thing. So the imaginary just kind of picks the minus epsilon. You have the squares, sum of squares at the denominator. Now, I want to integrate from A to B the integrand that we said, that we just analyzed. And so the integral from A to B of the imaginary part of the Cauchy transform is, and now you see here that I did something interesting. I switched the order of integrals. It was the integral from A to B, and then, well, there was the minus, which I'm putting outside, and then there was the integral over the whole real line of the integrand that we have here, and I switched the order of integrals. And whenever you do that, you should be careful how, how can I justify that? In this case, it's not so, mysterious, because the integrand is positive, and we're kind of used to the fact that we can always switch summations or integrals where things are positive. Nothing can kind of get cancelled and so forth. But that's in Riemann integrals or in sums. Here you have a Lebesgue integral, so I'm not sure you can justify it this way. The right way to justify this is using a Fubini's theorem, which I didn't cover, but let me just say one thing about it. So Fubini's theorem tells you that if you have, before Fubini's theorem, if you have two measures, you can define the product measure in exactly the way you think you can define a product measure. And when you have a product measure, you can have like a two-dimensional integrals, right? You can integrate over two variables. And Fubini's theorem tells you under what conditions, and I'll tell you what are the conditions, you can the integral according to the product measure is the same as first integrating according to x and then according to y, or the mu t in this case. And if the condition holds, then you can, and the product measure, you can integrate according first to x and then to y. Then you can also integrate according first to y and then x. And ignoring the product measure in the middle, Frobenius theorem in particular tells you that you can change the order of integrals. And the only requirement is that the function that you are looking at, the function on the two variables, is a Lebesgue measurable. Everything here is continuous, and there shouldn't be any problem here with that. And secondly, and that's fine in our case, the sigma algebra that you're considering should be what's called sigma finite. And this really means that you can cover the sigma algebra by countably many measurable sets, all of which have a finite measure. So the reals is such an example, right? Because you can take unit intervals, countably many, each of them has a measure 1 according to the usual, the standard Lebesgue measure. And then this means that R is sigma finite, and definitely the interval AB is sigma finite, it's actually finite, and so forth, okay? So if you want to look at the reference, check Frobenius theorem for justifying this equality. But yeah, I mean, I wanted to cover that, the measure theory part of the course, but you know, yeah, you only live once, you can't do everything. Okay, but from this point, I mean, if you look at this integral, you could have looked at it before, but now, you see, if you look at this integral, which you didn't look before, because now the dx is kind of attached to this thing. You're first integrating according to dx. Then this integral may remind you from your high school days, or I don't know, the arctangents function, right? More precisely, we know that the primitive function of this function is the arctangents function. So we just need to do a slight change of variables. So let's define y to be x minus t over epsilon. And if you do that, you can kind of easily verify, and the calculations are here, that the integral that we are looking for is exactly this thing. Right, a is now a minus t over epsilon, same for b. And then you just change variables, and that's what you get. Really, the things that we are looking at is, up to the -1 over pi normalization that we are ignoring. What the integral that we are looking at is equal to integrating over R this function against the measure mu. Okay, so that's the function we got. And just to remind you, this is the arctangents function, right? It approaches pi over 2 as you go to infinity, and minus pi over 2 as you go to minus infinity. So to recap, we just proved this thing. We proved that that the things with inside the limits is the same. So in particular, the limit as epsilon goes to infinity from above of this integral is equal to minus the limit of epsilon goes to 0 from above of that integral, right? Now, what I want to do is to switch the order of some of integral and a limit. And to this end, I'm going to use the theorem of dominant convergence. So what I'm going to do is I'm going to define the function fn, n is 1, 2, and so forth, to be arctangents of b minus tn minus arctangents of a minus tn. Right, these are these things that appear here, but I want countably many functions, so I'm replacing epsilon with like 1 over n. Each fn is clearly measurable because it's a continuous function in T. Okay, A and B are fixed, and n is fn. So each of them is measurable. If we will show that also their limit function is measurable, and that all of the fn's and f itself are dominated by some integrable function, in particular, we are just going to choose the function 2, then we can invoke the theorem of dominated convergence to justify the switch of the limit of this limit and that integral. Right, so let's see. So what the really interesting question is, what is the limit of fn? So let's see. So let's go backwards. Actually, it will be easier. And I need to understand the limit of fn, and there are 5 important intervals or points. So first of all, what happens when t is larger than b? So when we're here. So when t is larger than b minus t is going to be negative, right? And also definitely a minus t is going to be negative. It's going to be a smaller value. And so these are negative values. So maybe they sit here. And then as you divide by epsilon or multiply by n, what will happen is that and take n to infinity or epsilon to 0, they are both going to go to minus pi over 2. I mean, the arctangents of these are both going to approach minus pi over 2. And so their difference is going to be 0. Right, so what I'm saying is that the limit function f is 0 past b from the right. And same goes for the value t, which is smaller than a, because when t is smaller than a, let's go here. When t is smaller than a, it's also smaller than b. So both a minus t and b minus t are positive. And then when you divide by epsilon or multiply by n and take it to infinity or 0, depending on whether you're on the n or epsilon version, they are both going to, the arctangents in both cases is going to approach pi over 2, and the difference is going to be 0, right? What happens when t is a number that's strictly between a and b? Then in this case, b minus t is going to be positive, right? Something here. A minus t is going to be negative. And then as you take epsilon to 0, then one of them, the b minus t thing, is going to go to pi over 2, and the other one is going to go to a minus pi over 2. And you're subtracting the minus pi over 2 from pi over 2, so you get a pi. Right, so that's this pi. Or in this figure, it's this thing. So when t is strictly between a and b, then you have that f of that t is pi. Now, actually, when t is exactly a or exactly b, you get some slightly different behavior, and that accounts for the weird atoms that appear in the statement of the form of the theorem. So, for example, when t is, let's say, when t is a, in this case, when t is exactly a, then a minus t is 0. So arctangents of 0 is 0, and no matter what epsilon is, it's still 0. It remains 0. It doesn't go to plus or minus infinity. So you subtract a 0 from what? So when t is a, that's the case we're considering, b minus a or b minus t is positive. So it's something here. So it's something here. And you take that to infinity because epsilon goes to 0. So you get a pi over 2 minus 0, right? So that's why f of pi over 2, sorry, f of a, and similarly f of b are going to be pi over 2 and not pi. So really, this is the limit function. Okay? And you can easily see that this limit function, as well as the arctangents that you have, are bounded by 2. Maybe we need more than 2, because the arctangents is most pi over 2, but the subtracting can give you pi maybe. So let's call it 20 and be on the safe side. But all the fn's and the f are bounded by a constant. The constant function is integrable, obviously, and therefore you can invoke the theorem of dominated convergence to justify the thing we're going to do now, which is the switch, the limit, and the integral order. Namely, the limit of this integral which, as we said, is this thing, that's just a recap, is now equal to the integral of the limit, and we just figure out that the limit is exactly this nicely looking function, and this nice looking function is really a step function or a simple function, and we know how to integrate such functions, right? So you get a pi, which is the value of this interval, times mu of the measure of the interval, the open interval AB, and then you get pi over 2 times the measure of the singletons. And all in all, after dividing by 1 over, or after dividing by minus pi, you get the statement of the theorem that minus 1 over pi times this limit is equal to mu of AB plus half mu of the two atoms. Okay, that's it. But you see, we had to use kind of much of what we learned, how to integrate simple functions, the dominated convergence theorem, Fubini's theorem, which we didn't really cover, but I think we're fine, and so. Now, one remark, I still didn't told you how to really get mu of, like, technically speaking, mu of the open interval, because these two annoying atoms were there, the actual A and B. But the point is that you can show that there can only be countably many atoms, namely countably many singletons in a probability measure whose measure is non-zero. And so if you want to figure out what's the measure of AB, then okay, so there are countably many problems that you kind of need to avoid, but you can always consider a sequence of intervals that, in a sense, converge to the interval AB, and none of them has an atom, because there are only countably many atoms. They are not dense, so you can kind of avoid those. Okay, so to recap, Stieltjes inversion formula tells you that you can indeed restore mu from the Cauchy transform. Now, I should say that usually, not always, but usually in our setting, our cases, G mu is going to be continuous as it approaches the real line. And so the limit is going to be, it's a limit, but you can just essentially evaluate at epsilon equals 0. So what we did so far was to say how to restore the Cauchy, sorry, the distribution from the Cauchy transform. Now I want to relate the Cauchy transform to the moments of the distribution. Okay? So this is the theorem. It's a much simpler theorem than the Stieltjes inversion formula. And it says the following. It says, suppose mu is compactly supported. Now, when I say compactly supported, I mean that the support of mu, which is always really in our case, is closed and bounded, right? So the support is, say, maybe a finite interval, closed interval, okay? And in particular, let's say that R is some number, positive number, such that the, I think that should be minus R, right? Such that the measure outside of the closed interval minus R is 0, okay? Then what I'm claiming is that you can expand, Taylor expand the Cauchy transform outside of that interval, but really, in a sense, at infinity or around infinity, like we talked about when we talked about complex analysis. In particular, the Cauchy transform is this thing, right? It's a Taylor expansion, in a sense, around infinity, as long as you're far enough from the origin, where, interestingly, the coefficients are exactly the moments of the distribution. Okay, so there is a slight shift here, but Mn is the coefficient, the nth moment is the coefficient of 1 over n to the n plus 1. So let's just prove that, and then let me philosophize about it for a second. So the proof is very simple. So you're taking, let's take any z that is indeed has a modulus strictly larger than r, and let's consider any t that's smaller or equal than r. That's going to be a t in the support of mu in a second. But for now, let's just take t that is smaller or equal than r in absolute value. Then the integrand of the Cauchy transform, 1 over z minus t, you can write like that. You can pull out a z from the denominator. And now, since t over z has modulus which is smaller than 1, because z has modulus which is larger than r, strictly larger, and t has a modulus which is smaller or equal to r, you can, I mean, this geometric series converge uniformly also to that, so you get this equality. And let me just put the z back inside so you get this thing. Right, that's before taking the integral. That's just per t and per z, of course. And in particular, it means that for every z that's around infinity that has modulus larger than r, and again, it's c plus actually, because you don't evaluate the Cauchy transform at c minus. The Cauchy transform, which is just the integral of 1 over z minus t against d mu t, is this thing. I just kind of copied what I wrote before, but now I'm switching the order of summation and integration. Okay, and again, that should be justified. And how would you justify that? When, if you remember, we talked about series that you can change the series of positive functions with an integral as a corollary of the monotone convergence theorem, right? Because as you add more and more summands, you increase, because everything is in a negative, you increase the sum, so you get a monotone sequence like that of partial sums. Here it's slightly more, it's slightly different, because here we are talking about complex valued functions, and the monotone convergence theorem was about real valued functions. But you can kind of easily prove a little variant where you only assume that the modulus rather than the actual numbers are monotone increasing, or you can look at the real and imaginary values. I leave it to you. It's a fun exercise that it's not fun, but it's an exercise that will justify switching the order of summations and integration. But when you do that, when you switch the order of summation and integration, the integral passes 1 over z to the n plus 1 because it integrates according to t, and you get exactly what we said, right? It's like this is the moment, the nth moment of the distribution. You get 1 over z to the n plus 1 here. So let me kind of philosophize a little bit about it. So this is the picture I have in mind, right? It's kind of over dramatic, but this is the picture I have in mind. So you have the upper half of complex plane, and G mu is defined everywhere there. It's an analytic function there. What's cool about it is that as you approach the real axis, which I like to call Earth, like, you know, the floor, then while doing the right thing, you can get back the distribution, the measure itself. And on the other hand, as you go, as z goes to infinity, or really, as long as z is large enough, G mu takes the form of a power series or Taylor expansion around infinity, where the coefficients are the moments, right? So I like to call it the heaven and earth theorem. No one calls it like that. So you know, at the skies you have the moments, and at earth you have the measure, and the Cauchy transform is defined everywhere, but it takes that form, the moments form upwards and the measure form downwards. Now in free probability we are going to work with moments. As you remember, star probability spaces and so forth include moments. And so you would like to say that if I understand moments, I can get back the distribution. And the way to do that is to work with the Cauchy transform. Okay. Right. So maybe let me reiterate what I said last time in the example that we're going to do next time. which I already talked about a little bit. G mu is actually an integral that's defined everywhere here. But as I go to infinity, as I move away from the real axis significantly enough, I can actually see that this integral takes the form, like the local form of a Taylor series expansion, where the coefficients are the moments. In our example, the moments are going to be the Catalan numbers, so we really understand what's going on there. And from the reconciliation of the Catalan numbers, we are going to derive a function and equation that this function satisfies. Okay? Some quadratic equation. We are going to solve that quadratic equation and get two solutions. One of them is not interesting, you'll see. And the other one, again, you just looking at it, you see that it is defined in a domain that's larger in the entire hypergraph complex domain, even more than the Taylor expansion and even than the integral itself. Right? For example, in particular, we will see that the function that we get is continuous on the real line, at least not on, except for 2 points, but on most of the real line, which is unclear from looking at the function as the integral of 1 over z minus t against the measure. And so this magic of analytic continuation, right? You start with an integral that's defined everywhere, you move to this local view that you understand better because you understand the moments. You do, from that, you see that your function satisfies an equation, a functional equation. You solve the functional equation to get a solution which analytically extends the power series expansion, but in particular, but also not in particular, but also the function you started with, the Cauchy transform. So you look at that solution, it's analytic continuation. So in a sense, it's the same thing, but with a larger domain as the function you started with, and that will, in particular, will allow you to actually evaluate this thing, which as similarly has poles in some of these points at those points. Okay, so that's next time, but I hope that me reiterating it again and again, different stages of your learning will help you digest it before you'll see it. Good. So I think I'll do that next time. Good. You know, let me just say it here because it's good to say it now. That's the right context. So you can easily show, and that's just a technical thing that we'll need, that z times the Cauchy transform of any measure, as z approaches infinity in modulus, approaches 1. Okay, that's going to be useful. Essentially, for picking the right solution in a quadratic equation, you're going to get two solutions, and that's a nice test to see if you how to choose the right solution. But this one is really the one of that comes from the fact that you are looking at a probability measure. So how do you see that? Well, z times the Cauchy transform of z, because z is large enough, you can Taylor expand. I mean, you only care about z, which is large enough, because you're looking at the limit anyhow. So you can Taylor expand g mu z using the moments, as we just showed. But now you multiply by z. So by multiplying by z, actually you get that the nth moment is actually divided by z to the n and not by z to the n plus 1. So you have m0 plus m1 over z and so forth. And now taking z to infinity, only m0 survives, but m0 is really 1 because it's the 0th moment. It's like the measure integrating over the measure, like the one function over the measure, which is 1 because mu is a probability measure. Okay, that's just a technical thing that we'll need. So next time, we are going to go back to our example and see how we can use the Stieltjes inversion formula to get the analytic distribution from the Catalan numbers. Good.